We'll wait for a few more minutes for others to join. All right, let us start. So welcome everyone to the week 5 tutorial of the subject fluid mechanics. I hope everyone has been regular to their lecture videos by the prof on the Nptel portal. Apologies for the last 2 week uh, lectures to be postponed because of some of my professional commitments. So I have to uh, postpone them for today, and next lecture will be on the Sunday as well, a day after tomorrow. So yeah, I hope everyone is regular to their assignments as well. So those who have registered for the course and those who are going to give the examination, they have to complete their assignments. And in the last lecture tutorial, we had finished up with the atmospheric pressure, where we were dealing with the conversion of one liquid column to the another. And then we saw units of pressure and atmospheric pressure. And I hope you, if anyone of you have missed the lecture, you would have been able to check out my YouTube video tutorial, which I've uploaded on the YouTube channel. So my YouTube channel name is Nptel with Varnit. And those who have registered, they get the sheet from the NPTEL team about the links of each and every YouTube channel, each and every YouTube tutorial of this course. And all the PDF notes are available in the sheets sent by the Google Drive link sheet sent by the NPTEL team, as well as in all of my video descriptions you will find that. All right, so let me share my screen. Let us start with the week 5th tutorial. First of all, just hold on. Okay, so I expect that now my screen is visible. Share screen. Why is it share screen? I think some new feature has added on. Like, just hold on, please. So am I audible? Anyone can confirm me, please? I'm clearly audible. Share screen. Screen broadcast. Is my screen visible now? Can anyone of you confirm? Not sure why it's not. Okay, now I think it would work. Just bear with me for a few more seconds. Now it will start broadcasting. I expect that. Yeah, that works fine. Great. All right. So is my screen visible now? Anyone can confirm? Pragya, am I audible? Is my screen visible? Can you please unmute yourself and tell me? Okay, all right. So let's turn on my camera as well. Yeah, okay, thank you so much. So let us start. So the topic for today is absolute pressure, gauge pressure, negative gauge pressure, which is basically vacuum pressure. So topic is, we're talking about the different kind of pressures and how to measure them. Absolute pressure, then gauge pressure, negative gauge pressure, that is nothing but your vacuum pressure. So don't worry about the notes, you will get the PDF after the class, but if you want to make simultaneously the notes, you get the same. So we are living on a planet Earth. Okay? So if you are living on a planet Earth, we are experiencing some atmospheric pressure because there is some atmosphere in our surroundings. So the pressure by the atmosphere is called as the atmospheric pressure. Okay. So suppose I draw like this, and we are somewhere standing here. So we are experiencing some pressure that is the atmosphere. The atmosphere, and this is your planet Earth. Okay. Now, to measure the gauge pressure, we have some instruments. Okay. So gauge pressure is nothing but the pressure above the atmospheric pressure. Above the atmospheric pressure. So suppose I have an instrument like this. So there is some pipe, flow is happening inside a pipe. Okay. And some device I have put on the pipe. Okay, one end of the pipe. And it's like a dial kind of device. Okay. So, and there is some arrow here. So starting from 0, you have an count like this, and there's some arrow here of this dial. Okay. So this is your basically a gauge. This is your gauge. Okay. And because of the flow inside the pipe, there is some pressure P. Okay. And this pressure, which will be measured from the atmosphere pressure, will be called as the gauge pressure. So we calibrate our device in such a way that our pressure of atmosphere is set to 0, and then we measure the pressure as per the pipeline flow inside. Okay. And negative gauge pressure is suppose, so if your 0 start from left hand side, so this was your, and it moves towards the right hand side, so all of it is positive gauge pressure. But suppose your dial is like this, so again I draw a pipe and it has some gauge pressure, negative gauge pressure. So suppose I have a dial pipeline like this. Okay. And again a pressure P will be there, but I don't know, it's a negative gauge pressure I'm saying. So what will happen? Suppose my dial is starting from 0 from here. Okay. If it's going towards the left hand side, my dial is going towards the left hand side, then it is negatively showing me the reading, showing the reading that is in negative direction. So that this is P gauge, and that is negative gauge. Okay, negative gauge. So let us again draw in a schematic form that what different kind of pressures are. So first of all is a very absolute 0 pressure, that is vacuum condition. Vacuum condition, that is your standard reference. So we say that it is 0, or you say that it is an absolute vacuum. Absolute vacuum. Above that, we are living in an atmosphere. So we have some atmospheric pressure till here. We have some atmospheric pressure till here. P atmosphere. Then above the atmospheric pressure, we have a condition that is gauge. That is your P gauge, measured by some device. And summation of P atmosphere plus P gauge is nothing but your total P absolute. That is your P absolute. That is total plus P atmosphere plus gauge. What is negative gauge? Below the atmospheric pressure, because we saw that in this device, if 0 is our atmosphere, and if we go below that, then it is negative. So we'll go below. So that is your negative gauge. So here is your P gauge, that is negative. P gauge, that is negative. If you just go below the atmospheric pressure. But what will be the absolute pressure here? The absolute pressure here will be, if I say at the same reference, my absolute pressure will be P absolute will be P atmospheric minus P, that is vacuum. This is gauge or vacuum pressure. Vacuum. You can say that this to be gauge or vacuum pressure. Gauge pressure or vacuum pressure. All right. So I think this schematic is very clear to you. We have a 0 datum pressure. We have an atmospheric pressure. Above that atmospheric pressure is your gauge pressure. The total of atmospheric plus gauge is absolute pressure. Below the atmosphere is your gauge pressure and negative gauge pressure. And from the zero, you can say it is absolute as P atmospheric minus P vacuum. And you have to keep it in mind that two terms, vacuum and vacuum pressure, are very different things. So vacuum is absolute vacuum, whereas vacuum pressure is this. Vacuum pressure is the negative gauge pressure. Okay, always keep it in. So I'll write a note here. That is, vacuum and vacuum pressure are different things. Pressure are two different. All right. Okay. Vacuum and vacuum pressure are two different. So if I say that 30 kilopascal of vacuum or 30 kilopascal of negative gauge, or I say minus 30 kilopascal pressure. So all of these are vacuum pressures only. Example, if I say 30 kilopascal of vacuum or I say 30 kilopascal negative gauge or I say minus 30 kilopascal pressure. So all of these are vacuum pressures only. Vacuum pressure, not absolute vacuum. All of these are vacuum pressure. All right. So we understood what different kind of pressures are. Okay. So I'll write some other points of the note. So first point was this. Next point will be the pressure measured from the atmospheric is known as gauge pressure. The pressure measured from atmospheric is known as gauge pressure. Okay. There can be both positive or negative gauge pressure, but there can't be negative absolute pressure. Always remember. There can be both positive or negative gauge pressures, but there can't be negative absolute because absolute is absolute vacuum, that is zero. Okay. But there can't be so today we will starting with very important topics also, pressure measuring devices. So please carefully listen all the devices and their workings as well. But there can't be negative absolute pressure. First of all, we are understanding what kind of pressures are there and how to measure these pressures. And the next point is gauges are calibrated as per their local environment. Gauges are calibrated as per their local environment. What do I mean by that? That if you are living in the northern area of India, that is the Kashmir, your atmospheric pressure will be something different. Whereas if you are living to the southern part, suppose Chennai, the atmospheric pressure will be different. Why? Because you in Chennai, you are near to the sea level, whereas in Kashmir, you are very high above the sea level. Okay. So you have to calibrate the gauge, your gauge device, pressure gauge device as per their local environment to set P atmosphere to zero as per that. So what do I mean here? Suppose I have two different kind of gauges. So I'll set a zero here of P atmosphere will be something different here. In Kashmir, Whereas a gauge, if I have in Chennai, so my zero calibration will be something different. And this will be your P dash atmosphere, some another atmosphere. You have recalibrated. Okay, so you are initially the same. If you take this Kashmir uh, gauge to directly to without calibration to Chennai, so it won't be this. Sorry, it won't be this. It would be somewhere higher because you are near to the zero. So you have to again calibrate back to the zero, okay, to the PX in Chennai. Recalibrate. Recalibrate. Okay. Okay. Now we have understood what kind of pressures are there. Now we will start with the classification of the pressure measuring instruments. Classification of. I hope there are no doubts in here. If you have any doubts, please ask. Unmute yourself and ask. All right. Next topic, classification of pressure measuring instruments. So what kind of pressure? So one is on the basis of the liquid column deflection, that how your liquid column deflects, and other is the on the basis of the elastic properties. So on the basis of elastic properties are like mechanical gauges, and if you have seen in your labs also, one of them is like a Borden tube kind of gauge. Okay. But I'll talk more about the basis of the liquid column deflection, which are classified like manometers, piezometers, and simple manometers are then further classified as per piezometer, U-tube manometer, single column manometer. Whereas the differential manometers are also there, which are U-tube manometer and inverted U-tube. And for each of them, we will understand the science behind each of them and how they works and how to measure the pressure from all of them. Okay. So first is on the basis of liquid column deflection. And second is on the basis of elastic properties. So on the basis of elastic properties are like mechanical gauges. Okay. And one of them is like a Borden tube kind of setup. If you have seen like the setup, I'll draw for you. So there are some scales. There is a device like this. Okay. And it is somewhat, sorry, it is somewhat looking like in question mark, reflected question mark kind of device. Okay. And you have a pointer like this in here. So, and it measures, suppose, your atmospheric pressure, the atmospheric, and pressure is from, if you are connected with some pipeline source or something, pressure enters. So P is greater than the P atmosphere here. P is greater than P atmosphere. And as per the condition, it will work. So this is your Borden tube device. Borden, Bordentube. Okay, Borden. So on the basis of liquid column deflection, there are manometers. There are manometers. And keep it in mind, they don't need any calibration, these manometer devices. So one is simple manometer, another is differential manometers. Simple and differential. Okay. So in simple, they are categorized as piezometer, U-tube manometer. piezometer, YouTube manometer. So I'll draw some device figures as well. So piezometer something looks like this. So there is a pipe which is connected to some tube. So flow is acting inside the pipe. This is the flow is acting from here, from the pipe. The pressure is measured by the deflection of the liquid here. Okay. So some deflection of the liquid will be here. Okay, and the flow is like this inside the pipe. So it's a cross-sectional view which is happening, and the flow is happening like this. Okay, and the tube is connected like this. So this is your piezometer. Next is YouTube manometer. Manometer. So YouTube is like if you have like this, a U-tube is there. U-shaped tube is connected to the pipe. Okay, and again there's some deflection will happen here, and the liquid is generally mercury. I'll explain why mercury. This will also come that why mercury is only chosen. And here some pressure P will be here. Similarly, here some pressure P is here. Here's some pressure P is in the pipeline. Okay, and next is single column. Single column manometer. Okay. So single column manometer is like something like this. You have pipeline which is connected to some large cross-section area, and it is connected to some tube which is in U shape. Okay. Again, some fluid will be here. Okay. And pressure P is here. All right. So I'll explain each and every of them in detail. First of all, let me write all of them. Next are the differential manometer. So there are YouTube manometer, inverted YouTube manometer, and micro manometers. Okay. So first is YouTube differential manometer. Something look like this. So YouTube manometer, YouTube manometer. So your device looks like this. So it is required to measure the pressure difference across two pipes. So here you see there are two pipes. Okay. One pipe is this side, one pipe cross section is this side. You measure the pressure difference across both of them. Okay. So there will be some liquid, there will be some deflection. Again, mercury is taken generally. Next is inverted YouTube manometers. In inverted YouTube manometers, inverted, you will just invert the above manometer, YouTube. So your pipes will be somewhat like this here. The tube of in the U shape will be like this. Okay. Again, some pressure P1, P2 is here. Pressure difference is there. P1, P2 is there. And here, instead of manometric fluid to be mercury, we take some gasoline or gas. You'll understand. So here, the pressure of the first pipe, required pressure of the second liquid, and inside the manometric liquid itself. Gas, I'll explain all of them. Why is it so? And the last is micromanometers. Micromanometers. All right. Now let's come to the piezometer, first of all. So a piezometer is basically a very simple tube manometer. If you see, a pipe is there and a tube is connected in here. Pipe is there and a tube is connected. So this is velocity. Okay, with velocity V it is. So it's a simple tube manometer, and if you see, both the ends are open. So this end as well as this end, both the ends of this tube are open. One end is open to the pipe, one end is open to the atmosphere. Okay. And it's one is where one end is connected to the pressure where you need to measure, and second end is connected to the atmosphere. And it is connected across the pipeline so that you can't measure the dynamic head of the flow across the pipeline. Okay. So your pipe is going like this, complete pipeline is going like this. Okay. And it is connected like this here. Okay. So your pipeline is going like this. This is a complete pipeline where the flow is happening, and it is connected like So you cannot measure some dynamic head, that is velocity head you cannot measure. You can only measure the static head. And it measures the gauge head of the liquid. Always remember, because atmospheric we don't consider here. So it's always measure the gauge head. After the atmospheric condition, it measures the gauge head. And we can't measure the vacuum or the gas pressure here. We can't, it's a disadvantage. We can't measure the gas pressure because gas don't form free surfaces. So the pipe should always carry a liquid inside it. It cannot carry a gas inside it, because if you carry a gas inside it, both the ends of this tube is connected to the atmosphere. The outside air will come inside it if the pressure is below the atmospheric pressure. So the outside air will mix in the pipeline. We don't want that. Okay, so you cannot measure the negative gauge pressures or the vacuum pressure, because gas leak into the surface, as well as it doesn't form the free surface, and it cannot measure the vacuum pressure. As I said, air comes into the pipeline. For a high pressure measurement, there may be large column deflection. So you need a very high length of the tube. Okay, you need a very large column deflection of lighter density liquid. So it is used for moderate pressure devices only. You cannot take this tube length. You cannot take this, I say, this tube length to be very high. It will be, suppose you have a space constraint in some of the devices, you cannot take the tube length. So it measures only the moderate pressures. So let me write for the piezometer first of all. The piezometer. So first is, it is a simple tube manometer. Its both ends are open. Its one end is connected to where pressure is to be measured. Pressure is to be measured. And second end is connected, is open to atmosphere basically. Connected. Open to atmosphere. All right. Next point is, it is connected across the pipeline. It is connected across the pipeline. Just hold on, please. So it is connected across the pipeline, so you cannot measure the dynamic head of the flow. So can't measure dynamic head of the flow in the pipe. Okay. The dynamic head is basically, you cannot measure the dynamic head of the flow. Next is, it measures the gauge head of the liquids. It measures the of the liquid, not air. Okay. To be liquid, I'm saying, not air or gas. Okay. Why? What are the disadvantages of it? First one, as I said, it can't measure the gaseous pressure. It can't measure the can't measure gaseous pressure. Why? Because it doesn't form free surface with the atmosphere. There is no free surface. Liquid and gas has some free surface of the liquid, but gas and gas doesn't have a free surface because gas doesn't form free surface with atmosphere. Atmosphere area. Therefore, gas leaks into the atmosphere. Therefore, gas leaks into atmosphere. If the pressure of the gas is higher than the atmosphere, then it will go outside the tube. Next, it cannot measure the vacuum pressure. It can't measure vacuum pressure. Why? Because if pressure in the pipeline, P pipeline, is less than the P atmosphere, then what will happen? The gas from the outside, that is your air, will come into the pipeline. This implies this is a vacuum condition, that is vacuum negative gauge. This implies air comes into pipeline. Inside pipeline. So outside air comes inside the pipe. And for a high pressure measurement, there may be large column deflection. So instead, like pipe is generally you wanted this line of pipe, but if pressure is very high, you need this much size of pipe, which is not of use. Okay. You have space constraints eventually in the machines. There may be large column deflection of lighter density liquid. Okay. Again, I'm emphasizing liquid. We can only measure liquid pressure. So it is used for moderate pressure measurement. So it is used for moderate pressure measurement. All right. I hope piezometer is clear. Crystal clear. Now we will talk some application-based part of it. Okay. Where we'll involve pitot tube inside the piezometer and all of that. So it measures the gauge pressures as we have seen. It can't measure gauge pressure, it measures the gauge pressure. So how it measure the gauge pressure? Suppose I have a device like this, if I give you, okay? Note, let me write the note here. So first of all, I have a piezometer like this. There is some pressure P inside the pipeline. Pressure P is inside the pipe. And some manometric fluid is not manometric fluid, the fluid of the pressure in the fluid inside the pipeline enters into the tube and forms a free surface with the atmosphere. So here it will be atmospheric pressure. Okay, here will be atmospheric pressure. So, and it is suppose this manometer is some at a height of Z, okay, from the data. So what we say, we cannot measure the atmospheric pressure from this. So that is why we use some another device that is a barometer. I'll discuss that also. So what happens? This liquid of the pipeline went to some height h, from the center level. Okay, and this is your head, and this head is set to be in terms, that is p of the pipeline p by w. Okay, that is rho g. So always we talk in terms of head. Head is p by w, that is p by rho g. Okay. So if I want to measure the pressure p, how will I write? So it will be, if you want to measure pressure p, whenever you are going above the sea level, pressure decreases. When you are going near to the sea level, it increases. So when you are going above, our convention goes like negative. If you are going below, our convention will be positive. So P then minus rho GH. The pressure, hydrostatic pressure is rho GH. So you are going above. So starting from point P, you are all the way going up. That is minus rho GH. And that is nothing but equal to your atmospheric pressure. That is nothing but equal to your atmospheric pressure. That is P. So P atmosphere. So your pressure inside pipe is nothing but P atmosphere plus rho G plus rho GH. So this is your absolute pressure. You have seen that absolute is atmospheric plus gauge. So this is your absolute pressure. Absolute pressure, P abs. If I want to say in terms of gauge, then your atmospheric pressure needs to be 0. So that is rho GH. So this will be your gauge pressure. Gauge pressure. This is your gauge pressure. If P atmosphere is 0, okay, and head is, as I've said, head is nothing but P by rho G from here. That is P by. This is your head. This is your head. Always gauge head, I should say, not head. I should say gauge head. And always we talk in terms of the gauge head. Okay. So piezometric head is nothing but the head P by W, that is P by W, plus your datum head Z, plus your datum head Z. So your total piezometric head will be P by W plus your datum head. So your piezometric head, right? Piezometer is measuring head is nothing but P by W plus Z plus Z, where this is your H, as I said, and it is called as static head. Static head. Because it is not moving now. Once the flow inside the pipe has come into this tube, then it has achieved some height h. That is your static head. That is your static head. And that Z is your datum head. Z is your datum head. Okay. And this completely is called as piezometric head. Okay. All. I hope no doubt still here. What is piezometric head? What is absolute head here? How we calculate the absolute head? How we calculate the gauge head from the piezometer? So suppose I have an instrument like this now. I have an instrument like this. It's seems to be a very complicated, but it's not a complicated instrument. So suppose my pipeline, suppose this can be at any of the circumferential point of it. Okay, and my tubes are here. My tubes are here. One tube is going from this side. One tube is going from this side. One tube is going from bottom. Suppose the tubes are all going like this. Okay, and this whole setup is at a datum Z. Okay. This is zeta datum, and it depends now which datum from where you are talking. Okay, the Z will from which place. So each of it has a manometric fluid with all of them having a level till the same. Okay. So this not manometric fluid, the fluid from the pipeline P. Okay. So all of them will be, because all of them are piezometers only. So from all of them, it will be the fluid will be there. Okay. So suppose I take this as my reference level. This was my reference level. Okay. This was my reference level. So I say that my this point, I suppose I take 4 points here, A, B, C, D. Suppose my first point is A, the second point is B, the third point is C, the fourth point is D. Where should I put my pipe such that my pipe can be here? The first position can be like this. My other position of the pipe can be like this, P2, or the third position can be like this. That is P3. Okay. The third position can be like this. So where should I put my pipe so that my pressure of the piezometric pressure should be same? So I think at any of the position, if you put the pipe either at A, B, C, D, okay, A and C are at same level. So A, B, or D, you can say. Wherever you put, the pressure will be same. How? Let us see. So suppose that this complete till here, the Z is this point here. My Z is Z3. Okay. This point is my datum is Z3. Okay. So if I put my pipe at point 3, so my datum is at Z3, and the hydrostatic head will be, sorry, my static head will be how much? Static head will be above this datum head, which will give me my total piezometric head. So this is my till here. Okay. This will be my H. This will be my H3. Get it? You get it? This will be my H3. So this is my static head plus the datum head. This gives me a complete piezometric head from the left tube. If my pipe is at position 3, installed at position 3. Okay. If my pipe is installed at position 1, that is P1. So my, first of all, datum head will be this much. My datum head will be Z1. Okay. Plus my other head will be how much from here till here will be till here. That is H1. H1. Okay. Got it. If my pipe is installed at position, so my pipe is installed at position 1, my static head will be H1. Now the third position, if I say either it is at point A or point C, it will be Z1 plus H1. If it is at point 3, then it will be H3 plus Z3, my piezometer. If I install my pipe at point B, then my point B is from the datum level is at, let me use some another color now. Suppose this is your point B. So this is at Z2. My pipe is at Z2. So this will be my color. Should use the color. This will be my H. So complete piezometric head will be Z2 plus H2. So if you see all the levels of these positions, suppose I say this is my position X, my position Y, my position Z, all X, Y, Z at the same horizontal level, and all are giving me the piezometric heads to be same from the datum. Okay, same from the datum. So we say that pressure in the pipe is greater than P atmosphere. Okay, either it's 1, 2, or 3 position. So total head of the flowing fluid, total piezometric head will be P by W. If I say piezometric head, but if I say total head, if I talk about total head, not piezometric head, suppose, what will be my total head from the Bernoulli? Total head of flowing fluid is P by W, that is the pressure head, static head, plus datum head, that is Z, plus that dynamic head V square by 2G. Okay, V square by 2G. My piezometric head is how much? Me use another color now. So my piezometric head is this much. Piezometric head of the piezometer. And piezometric head in all the cases, that is P1 by W plus H1 is equal to P2 by W plus H2, not H1 H2, sorry, Z1 Z2, Z1 Z2 is equal to P3 by W plus Z3. All are equal. So you install the pipe at any of the position, your piezometric head is going to be same. Okay. So and head isn't a function of the radius. It doesn't matter if you are at the same level. Suppose if I say I'm at the same level here, so it doesn't matter at any level you go. It doesn't depend over the radial direction of the longitudinal direction. So, okay. All right. So you can install pipeline for piezometric head. Install pipeline at any of the positions from A, B, C, or okay, C or D. Now we understood that from this complex problem, if you have three different kind of piezometers connected to a pipeline, all will give the same pressure. All will give the same piezometric pressure. Any doubts till here? Because I'm going to involve a much complexity inside it. That's why I'm asking. Any doubts, please ask at this point of time. Mohammad Venkateshwar, any doubts? Pragya, do you have any doubts? Please unmute yourself and talk to me. That's why I want to. Do you have any doubts or not? Pragya, do you have any doubts? Clear? Okay, great. Okay. Now let's come to the involvement of a pitted tube inside the piezometer. Okay. So suppose you have a just a second. You have a tank like this. It's this. There is some tank here. Okay. And it is filled with liquid. And it is connected to pipe. So one end is connected to a piezometer. Piezometer is something like a very narrow opening here, okay, from where the fluid enters, okay, and rise to some height. Okay. So suppose this was my reference level, and this is my data. Okay, this is my data. Fluid enters in here. So my piezometer will be giving some deflection, suppose till here. Fluid enters in. Okay, the piezometer will be like this. Suppose this is my velocity. The fluid is flowing from the velocity v. Okay, fluid is flowing at a velocity v here, and this is a point position 1. Position 1. So it is a piezometer. First of all, let me write. Okay, and it gives me some static head, that is P by W. Gives me a static head, that is H, that is P by W. Okay. Now this pipe is also connected through a pitted tube. this complete pipeline, and I install one pitted tube in here. So let me use some another color for. So I have a device that is okay. So I installed some pitted tube. Always make sure that the diameters of all the pipes are greater than the 10 mm. So no capillarity is taking place, okay, in any of the tubes, or either of manometer, piezometer. Okay, so diameter is always greater than 10. Suppose I have these 2 points. So my first point is 0.3 just outside the pitted tube, and the 0.3 that is just inside the tube. So what will happen? So again, fluid will try to enter inside that. This okay, the liquid will enter to inside this pitted tube, and this liquid will rise till when the head, or you say the energy, becomes equal, okay, and then only the fluid from the sides will go along from here. So why this? Yes. So fluid then only crosses this, but the fluid will come till which part? One is this, because it is something kind of a converging scenario. So fluid try to enter, they try to rise the level, plus you have stopped the fluid from flowing. Now what has happened? Some dynamic head has also incorporated inside it. Dynamic head has also incorporated, and that will make my level equal till here. So till here it was P by W. Till here it is P by W only. But from here till here, it is extension, so that your level of the reservoir is matched with that of the pitted tube. That is your V square by 2G, that is dynamic head. V square by 2G from the Bernoulli. So I've written the Bernoulli here now. From Bernoulli, I'll write here. From Bernoulli. Don't worry, we'll discuss this Bernoulli and everything later on as well. So it just says that the head, sum of all the heads is constant. Okay. For an incompressible rotational fluid, a lot of assumptions are there in this fluid. We'll discuss those things. So this is E square by 2G, a dynamic head. Let me write here dynamic head. And this total of it is your stagnation head. Why stagnation? Because you have stopped the fluid from flowing and it rose till a level of static plus dynamic head. That is your P naught by W. Naught stands for stagnation. That your velocity has come to 0. Stagnation means velocity 0. Stagnation head. Okay, stagnation head. Okay. And all of them are at a reference level of this 0.1 is at level Z. Again, 0.2 is also at level Z, because it's at same level. It is not inclined system. It's at same horizontal level. And this device is called as pitted tube. Let me write here. Pitted tube. Okay. All right. And it is always important. So what happened here at 0.3, first of all, the velocity became 0 at 0.3. That is why it is stagnation. So here, stagnation, that is V is equal to 0. Stagnation of fluid. That's why the fluid rose up extra. Okay. So what I was saying, what happened basically, the head converted into a dynamic head after you stopped the fluid. Okay. And stagnation head is sum of dynamic head plus piezometric head. Always remember that with the pitted tube, a piezometer will always be there. It cannot be only pitted tube because you don't know how you will see. I have made this with two different colors. This inside the fluid, but it is not two different colors. It is the same fluid. How you will be able to manage that? What till what level it is showing a piezometric head and till what level it is showing a dynamic? You cannot identify. It will be a same single fluid column. You can't identify till what reference level. That's why you always will install a piezometer along with the pitted tube, because from the piezometer you know that what is my piezometric head, you know what is my total stagnation head. So from the stagnation head you subtract the piezometric head, you get the dynamic. Okay, then only you get it. So pitted tube is always installed with the piezometric uh, piezometer. Okay. So for at the point 2, if I want to apply Bernoulli, my point 2 will be, let me write here. So my point 2 will give me a Bernoulli equation like this: P by W plus V square by 2G plus Z. And at point 3, my Bernoulli will be looking like this: P naught by W, not P by W, P naught by W. There won't be any velocity at this point. So 0 square by 2G plus Z. Why? Because this P naught itself has V square by 2G. P naught itself has this V square by 2G. That is why. So we cannot explicitly write again V square at that point 3 square by 2G. Okay. So let me again also write my P naught by W is nothing but P by W, that is piezometric head, plus V square by 2G, that is my dynamic head. So I'll write here, this is my stagnation head. Okay. This is your static pressure head. Static pressure head. And this is your dynamic head. My complete piezometric head will be total, or you say piezometric head, will be P by W plus Z. Okay, static plus data. Static plus data. So I'll again write static head. And this is your data head. So color code has made the same, so you understand. Okay, different and same. Okay, so we have different kind of heads. That is, so V square by 2G is again H. So we write as under root of 2GH. We write as under root of 2G. So we have different kinds of head. That is, first is piezometric head. Then we have dynamic head. Then we have stagnation head. Then we have total head. Okay. And total head is nothing but your P naught by W plus Z. Total head is P naught. P naught itself has P by W plus V square by 2G plus your data head. Okay. So it has static, total head has static plus datum plus dynamic. That is nothing but your Bernoulli. That is eventually your Bernoulli, which is always constant. So P naught by W plus Z. Okay. And P naught by W has P by W plus Z, which is piezometric head, and V square by 2G is your dynamic. I know it's a bit complex to understand in one go, but I've tried to make it as simple as possible to understand. Okay. You take 2-3 minutes of break, think about it, then we'll move to the next topic of vapor pressure. Okay, we'll take a 2-3 minutes of break. Just read about it once again. I'll open up this figure so that you can easily check. Okay, I'll join back in a few minutes. Okay, so let me write the last point in here. That is, PeterTube is always installed along with the piezometer. PeterTube installed with the piezometer so that from stagnation head we subtract, or you said total head. Let's check this. From total head subtract piezometric head to get dynamic. Okay, very important point. Let's come to the next topic of vapor pressure. Vapor pressure. Right, the heading, what is vapor pressure? Vapor pressure. So always remember that vapor pressure is always calculated through the experiment only. From experiments only you can get the vapor pressure. And vapor pressure or the partial pressure of the vapor is nothing the pressure exerted by liquid vapors on the liquid surface itself. In a closed container is known as a vapor pressure. And always remember that it is always at a given temperature. It is always at a given temperature. So saturation pressure or you say partial pressure of vapors exerted by liquid vapors on liquid surface in a closed container is known as vapor pressure. And it is always at a, remember, at a given temperature. If the ambient temperature changes, the pressure changes of the same liquid. Okay. So suppose I have a container like this. I have a container like this, and it is filled with some liquid. Okay. There is some liquid inside it, and it is at some temperature T. It is at some temperature T. Okay. So at a particular temperature, there will be some vapors of this liquid which will be formed inside the closed container. They will be accumulated like this here. Okay. And they will exert a pressure on this liquid surface itself. Their liquid pressure is exerting the pressure on its liquid. So this is the pressure which is exerted. That is your vapor pressure. Or let me write like this. Each vapor is exerting a pressure. And this is your vapor, PV. Okay. So let us say for a given temperature, you have a mercury inside this as a liquid. Okay. So there is a mercury liquid surface here. Okay. Because of that, there are some vapors inside that at a particular temperature, and there is some, because of those vapors, there is a pressure on that liquid surface. Okay. If you connect this, either you increase the temperature or decrease the temperature depending on that. If you increase the temperature, the liquid will try to evaporate and more vapors will form. More the number of vapors, more it will increase the pressure on the liquid surface. One way is this. Another way is if you connect it to some suction pump, okay, and if you take out the pressure inside, lower the pressure inside the container. Okay, so more and more again pressure vapors will try to form of this liquid because you have decreased the pressure in here by connecting it to a suction pump. Okay, and this again will form more vapors, okay? And more vapors will create more pressure. One another way is this. Okay, but if you decrease the pressure below its vapor pressure, okay, the pressure by sucking out, you decrease the pressure here below the vapor pressure of the mercury, which is nothing but 0.17 kilopascal at room temperature or 20 degrees Celsius. Then what will happen? All of this liquid will convert it to the vapor. there won't be any liquid free surface on which it will dissolve. So you cannot go below the vapor pressure of any particular fluid. Always try to. Okay. So I can say that for different temperatures, suppose you have 20 degrees Celsius. So vapor pressure of water is nothing but 2.5 kilopascal. But same water at 100 degrees Celsius will have eventually higher vapor pressure, more number of vapors will form. It will be 100 kilopascal, that is 1 atmosphere. Okay, the vapor pressure will increase, more amount of vapors will form. Okay. At 20 degrees Celsius, suppose I have a gasoline. So vapor pressure of a gasoline is nothing but 30 kilopascal. Whereas at 20 degrees Celsius, vapor pressure of mercury is least, that is 0.17 kilopascal. Okay. Now, if I say I'm using a manometer, some kind of manometer is there, which will come to our YouTube manometers, where we'll put the manometric fluid inside that. What kind of fluid should we use? Should we use gasoline? Should we use water? Should we use mercury? So it depends. So if I'm using a YouTube manometer to find pressure differential manometers as well, so I'll use mercury. Why? In differential YouTube manometer. Why? Because its vapor pressure is less. I don't want in the pipe of that, in the tube of that manometer, not the pipe, in the tube of the manometer, I don't want its vapor to form. I want the mercury to be as it is at the room temperature. So less amount of vapor should form, and they should not clog the surface of the tube as well. They should allow my pipeline fluid to flow, and they should be able to allow the manometric fluid to deviate or fluctuate so that I get the exact reading. I don't want vapors inside that. No extra pressure from the vapors. I don't want. Okay. That is why mercury is used in the manometers. Okay. So I'll write here. That's why mercury is used in manometer. Okay. So every liquid has its own vapor pressure for a given temperature. As the temperature increases, saturation pressure or vapor pressure also increases because more amount of vapors form. And if the absolute pressure, that is atmospheric plus gauge, is less than the corresponding temperature vapor pressure, so if the surrounding temperature is less than the vapor pressure of that liquid, then whole of the liquid will evaporate, and whole of the liquid will evaporate. There won't be any free surface, and this will lead to a situation that is cavitation. And this cavitation problem is my research of study in my PhD. Okay. All right. So I'll write few points. Yeah. Each liquid. So suppose I have a YouTube manometer like this. Suppose. So mercury is generally used here as a liquid, and the fluid flow inside the pipeline. Okay. And suppose this is at 20 degrees Celsius. Okay. That's why mercury is used. It's very clear. So each liquid has its own vapor pressure for a given temperature. Okay. Remember, for a given temperature, very important point. And as the temperature increases, this implies vapor formation increases. This implies vapor pressure increases. Okay. And if the absolute pressure of the surrounding, if absolute pressure of the liquid becomes less than the corresponding temperature vapor pressure, at that temperature the vapor pressure, okay, this implies it boils or evaporate. Okay, and this leads to a problem of shift. This leads to a problem of cavitation. So let us study what is cavitation. I hope no doubts still here. No doubts still here. Let's proceed to cavitation. So what does a cavitation situation is like this? Suppose you have a venturimeter device, which is a converging diverging kind of system. So a water is flowing inside this venturimeter. Suppose this is a reference into line V of water. So when it passes through a venturi, the velocity increases, pressure decreases, and the temperature suppose is at 20 degrees Celsius, which we are working on, the room ambient condition. So at this position, there are the chances that velocity is very high and pressure drops because of the high velocity, the pressure drops and there may be formation of vapors, okay, of this water vapor forms here. And when these water vapors are further carried away at such high velocity to a lower velocity zone and a higher pressure zone. Here the velocity is high, but pressure is minimum. Let me write using some of the velocity is high and pressure is minimum. Okay, and when these vapors travel here, okay, this forms of air bubbles or vapors. Okay, these are your bubbles or vapors. And because the surrounding liquid pressure has increased and velocity has decreased of this liquid, they impact this liquid this liquid impact this bubble at a very high pressure now. And when the high pressure bubbles implodes because of the high pressure of the liquid, the bubbles implodes and the bursting happens. Because of that bursting, the plate or the material of this venturimeter or any blades, you have a pump at your home, you have gas turbines, you have big steam turbines, blades are there. These bubbles hit at very high pressure on these surfaces and they erodes the material. Okay, and that leads to this scenario is phenomena is known as cavitation. In your pumps or venturimeters, you will see this. Okay, or the blades. So if P vapor, so what is happening here? If P vapor pressure of water is 2.5 kilopascal and the pressure becomes less than the 2.5 kilopascal. So what happens? Vapor bubbles forms. Okay, vapor bubble forms. So, so in the fluid flow, if the absolute pressure I'm talking about of flow becomes, not the gauge pressure, of flow becomes less than vapor pressure, fluid at corresponding temperature, then the bubbles are formed. And if these bubbles carries in a region of high pressure liquid, the bubbles get collapsed and erodes the surface. Surface of the material. Okay. And this phenomenon is known as cavitation or pitting. Okay. Pitting or cavitation. Okay. So it happens at the suction side of the pump or exit of the turbines or siphon tubes. All right. I hope this is clear. Now, how to measure the atmospheric pressure? I said that we use a device that is barometer. So we'll talk about barometer. Very simple device. So it is nothing but it is an instrument which measures the local atmospheric pressure. Local atmospheric pressure, and it is a simple kind of piezometer. It is a simple type of piezometer. Whose one end is closed. One end is closed. So what happens? We have a beaker like this. Okay. We have fluid inside this. Okay. We take an inverted tube. We take an inverted tube, and this liquid is nothing but mercury. Okay. So what happens? The mercury enters, and first of all, we create a vacuum inside this tube. Okay, we create a vacuum inside this tube, and as soon as we create the vacuum, the vapors of the mercury forms. If we take the pressure below the vapor pressure, eventually less than 0.17 kilopascal, then the vapors of the mercury will form, and then we lock that tube. Okay, then we lock that tube. So what happens? It will rise till some level. The mercury will rise till some level. Okay. And there are some fresh vapors of this mercury. So till what level it rose, that gives us the P atmosphere. And here it is P vapor of mercury. Okay. And it has rose to a level of, suppose, H. It has rose to a level of H. So this is nothing but your atmospheric pressure. The pressure because of the atmosphere has created up on this liquid mercury surface, free surface, and it rose the mercury in some level H. All right, very simple kind of device again. So how you measure the pressure inside it, how you measure the pressure is, suppose the pressure I want to measure. So starting from this level, P vapor, if you go down, that is rho GH is equal to P atmosphere, is equal to P atmosphere. So I'll write it here. P vapor of mercury plus W or rho G of mercury into height H is nothing but your P atmosphere. Okay. So W of Hg into H is P atmosphere minus PV of Hg. And you know that vapor pressure of mercury is very less, 0.17 compared to the atmosphere. That is 0.17 kilopascal and 100 kilopascal. Very smaller value, can be neglected. This can be neglected. So this gives you again a pre-atmospheric value only. So you know what is the H value, you know rho g value of this, you get the atmospheric value of the atmospheric pressure of that local environment. So advantage of mercury in a barometer is that high specific weight, rho g, that is high, and lower vapor pressure. Okay, that is why we use mercury. Advantages of Hg or mercury in barometer. First is high specific weight. So because of that, rho g value is high, and you don't need a very high H value. That is, you don't need a very high tube of the barometer. In a smaller, we discussed this in the last class also. So high specific weight. And next is low vapor pressure. Okay. Now coming to the U-tube manometer. We have finished up with the piezometer, application of piezometer. We have understood vapor pressure concept. We have understood what is cavitation. We have understood the atmospheric pressure calculation using barometer. Now coming to the U-tube manometer. U-tube. U-tube. So here you have a manometric fluid inside it. So you have a pipe in which the fluid is flowing. You connected this with the device that is U-tube in shape. Okay. So, okay. And you have some manometric fluid. Reflection will happen. This is nothing but your mercury. So fluid is flowing in the pipeline. That fluid has will come till here. Then you have a mercury. So suppose fluid is flowing with some velocity v across this. There is a pressure P here inside this. This is at a height till suppose y1. Okay. So from this reference level, if I say, okay, so suppose this is x, this much of it is x, this much of it will also be x from the geometry. And suppose this is y. This is y till okay, y1 and y. How we will calculate the pressure again? Using our same sign conventions. Starting from here, P, you are going below, plus rho g y1, then you are again going below. So rho will be different this time. The fluid in the pipeline is of some different rho. Fluid in the of the mercury is some different. Okay. So let us say this mercury has a rho, or this fluid has a density of liquid has density rho L, and this is manometric fluid that is rho M. Rho manometric fluid, density of the manometric fluid. We say that P plus you are going down, so that is rho L G into y1. Then from here till here you came, then further you will go till here. Okay, that is rho m gx plus rho m g into x distance. Okay, from here to here you go. Now you go above. So this level is same, doesn't matter rho m gx. Hydrostatic pressure is same across the horizontal level. We have discussed in our previous tutorial. Then you go above. When you go above, the pressure decreases, but the liquid is same. The manometric fluid is same here. Okay, so it will be minus rho mg, and the distance is also x. Then from here you further go above till y distance with the manometric fluid rho m minus rho m g y, and it is open to the atmosphere here. So this is P atmosphere. Okay, equal to P atmosphere. point to note here is that this and this cancels out. So what we can say that if we are in the same fluid at the same levels, we can directly jump off. This fluid is same till here and both are at same level. So from directly rho gm rho L G Y1 and then directly jump here and minus rho G rho mg y you can skip this rho m elevated fluid because the elevated fluid is skip this step. So your final pressure inside the pipe is P atmosphere plus rho mg y and this is y1 minus rho lg y. So the final pressure is this, and if you want to have a gauge pressure, you need to take atmosphere to be 0. If P atmosphere is 0, so P gauge will be rho mgy minus rho lg. This is absolute. Okay, all right. Any doubts still here? No doubts. Now coming to the single column manometer. So we understood U2 manometer. Single column manometer. Okay. So here you can measure gas pressure also because you have a manometric fluid and there won't be leakage of the outside air because this air can't entrap from this liquid, a manometric liquid. Also, this air won't go inside this liquid. So you can measure the air pressure also using the manometers, not only the liquid pressure. So it will be a fluid. Okay. Now coming to the single column manometer. So single column manometer is like this. So I have connected to some thing like this. Okay. So I should drag it to the left. I'll make one more figure here. I'll do the copy of it. I know you guys can't do. It's all right. Paste. Okay. I think I need to drag it a bit more. Okay. Now I have the same analytical devices. So the area of this is A, whereas the area of the small tube is small a. Okay. And suppose I have a manometric fluid filled from here and the level will be same until unless I connect it to the pipeline. So I connect this one with the pipeline now. This is the pipeline with the pressure. So here the liquid have that's equal. Again, this will fall down eventually. This reference level is going to fall down. Okay, so this liquid is going to fall down by some distance, suppose delta H. Okay, and this there will be a rise up here as well. Okay, so there will be a rise, suppose still here of this manometric fluid. Okay, so this must again delta H. Let me write this much is delta H plus some height H as well, plus some height H as well. Okay, some height H as well. And always remember that pressure in the pipeline is greater than atmosphere. All right, because you don't want any kind of impersonal. And but here pressure is P atmosphere only, both ends, because both are open to the atmosphere. Okay. Nothing is connected so far. So as soon as you connect the pipeline, that happens. So whatever the volume from the left after connecting the pipe in here, whatever the volume the left has gone down, the volume of the liquid or manometric fluid has risen here. So what I can say that volume is nothing but area into height. So capital A into small delta H is equal to whatever liquid have rose above is small a into small h. So whatever volume has risen up, that is the same volume that has dipped up. The same volume that has dipped. Okay. All right. So from here you can get the height h, that is a into delta h by small a. Okay. Again, you will apply the law. That is, if you are going down, starting from this point P, you are going downward, plus rho L G Y. Suppose this height is y from here till here. Okay. So this length is from here till here, it is y. So it will be P in the pipe plus rho L G Y. So from here again rho L G delta H, because liquid is different here, plus rho L G delta H. You cannot directly jump off from here to here, because here till this much is liquid of the pipe, but here liquid is of nanometer. Then what you can do, from here to here you can jump directly. You don't need anything, because the liquid is manometric fluid only, and then you go above. So that is minus rho mg delta h, and minus rho mg small h is equal to, you say if it's open to atmosphere or not, depending on your choice. So P atmosphere. Okay. Here it is. If you want gauge, you subtract it out. From here, you get the P, and the H value will come from here. Put this H in. All right, in terms of delta H. Now let's come to the next topic of sensitivity of the manometer. Sensitivity of the, what do you mean by sensitivity? So sensitivity is the ratio of manometric liquid deflection in inclined tube manometer to the U-tube column deflection in water for same pressure difference. Let me write it first. It is the ratio of manometric liquid deflection in inclined tube manometer to the U-tube column deflection in water for same pressure difference. Okay, always remember, for same pressure difference. So if I have a pipe like this, my pipeline is like this, and on the right hand side it is connected with a inclined kind of, whereas on the left hand side it is connected with vertical kind of. Okay, it's basically a simple piezometer here, right? Okay. And both are at same pressure difference, so eventually this and this level is going to be same. So we still here, so that my level is same. Okay, and this is my center level. Okay, this is my center level. So I say that this is the length L till where it rose. Length L from here, inclined length L, and this is your height H vertical. And this again will be also your vertical height H only. Okay, and this is at an angle, this inclination is at angle theta. Okay. So what is sensitivity? Is L by inclined ratio. It is the ratio of manometric liquid deflection in inclined tube, that is L, to the U-tube column deflection, that is H, L by H. And from the geometry, we know that L by H is 1 by sine theta. So if theta increases, if theta decreases, sine theta decreases, sensitivity, that is capital S, of increases. Okay, sensitivity increases. So we can't have a lower value of theta. We should have a vertical. Higher the value of theta, the lesser the sensitive the device will be. Okay, so theta is always at least greater than 5 degree. Okay, 5 degree. Also, sensitivity is inversely proportional to specific gravity. Okay, so if you decrease the specific gravity, your sensitivity of the manometer is. Another point is sensitivity is also, if I have a device set up like this, suppose single column kind of manometer. So diameter of this is capital D and this is small d. Sensitivity also depends over 1 by small d square by capital D. So sensitivity depends on all of this. And you have to have some assumptions always for a manometer, that is fluid is always static inside a manometer, fluid is always incompressible, and there won't be any capillarity. As I told, the diameter of the tube should always be greater than 10 mm. Diameter should always be greater than 10 mm. Okay. So assumptions for manometers. First is fluid is static. Second is incompressible fluid. And third is negligible capillarity. That is D is greater than 10. Okay. Tube diameter is greater than 10. Now let's come to the differential U-tube manometers and inverted U-tube manometers. Okay. U-tube. So again, you are set up like this. It is used for calculating the pressure difference between the two pipes. You have one pipe, another pipe. You need to get the pressure difference. Suppose this pipe has a pressure P1 and this pipe has a pressure 2, and it has some manometric liquid that is have density rho m, generally taken as mercury, but not specifically always. So suppose the deflection from here till here is y1, from here till here is y2. Okay. So suppose this is your reference level and this switch will be how much? Is y from. This is 1. So the density of this will be rho1, the density of this will be rho2. Again, you apply, start from here, P1 plus rho1 gy, you directly jump off, minus rho gy till here, then minus rho2 gy. Okay. So I'll write like this, P1 plus rho1 gy1 minus rho m gy minus rho 2 G Y2 is equal to 0, or is equal to P2, sorry. This is a pressure P2. So pressure difference P1 minus P2 will be how much between the two pipes? Will be rho 2 G Y2 plus rho m G Y minus rho 1 G Y1 mg. Okay. So if I say, can I write this as like this? I put a sign here. So this much is pressure in pipe 2, that is pressure 2, and this much is pressure in pipe. Okay. Not pipe 1, pipe 2, sorry, my bad. This suppose is a position A, and this suppose is a position. So here it will be PA, this will be P. Okay, PA and PB. Pressure at A is this much, pressure at B is this much. No, this is also, I think, rho m won't be there. So let us not get confused. Let us leave this much. Otherwise, you guys will get confused. I have to make this point separately. Okay. Okay. So the pressure difference, you should understand that the pressure difference P1 minus P2 is this much. Okay. And if here it is said that P1, that is why it deflected like this. P1 was greater than P2, and rho density of manometric fluid should always be greater than density of rho 1 and rho 2. Okay. Otherwise, the manometric fluid will go inside the pipe. Okay. It's a heavier fluid. Okay. So this was our YouTube manometer. Now inverted YouTube manometer. Inverted. So right here for getting pressure difference in two pipes. Okay. Inverted tube is again same scenario, but here if your pipeline has a, suppose a you want to have a pressure difference you want to calculate which is very low between the pipeline. So we said that the pressure difference was high, maybe moderate or high in here. But if you have a pressure difference very low, then what will you do? Very low kind of pressure difference scenarios there. So in that scenario, you use inverted U-tube manometer. Okay, why? You will understand now why we use this. So suppose again here P1 and rho 1, P2 and rho 2. So manometric, this is your fluid from the P1 pipe, and this is your fluid from the P2 pipe. Okay, and the manometric fluid this time will be gasoline here. Gasoline. So that the gasoline can easily displace if the pressure difference is very low. If the pressure difference is very low, if I take mercury, the mercury will be still there. It won't move. That's why we take a gasoline. Okay. So suppose this is at a distance of y1. Okay. And this is at a distance of y2. This much is how much? This is y. Again, you use start from here, go till here, then it's a jump off, downward and P1 minus, you are going above rho 1 G Y1, then you jump off and go down rho M G Y, because the liquid is in gasoline, minus rho 2 G Y2, sorry, plus is equal to pressure in 2. So pressure difference, which is very less, that is P1 minus P2, will be rho 1 G Y1 minus rho 2 G Y2 minus rho mg y. And if suppose you have very high pressure differences, then you can't have this tube length to be very big. Okay. Then in that scenario, you use multi-U-tube manometers. Multi-U-tube manometers. Okay. So I'll write a note here. Multi-U-tube manometers are used for high pressure differences because their fluctuations will be very high in a single tube. So we use a multi-U-tube manometer kind of scenario where my first pipe is like this. So my first U will be like this, then the second U will be like this, and my third U will be like this. And this is connected to the other. Okay. So P1, P2. Here again, rho 1, rho 2. Okay. So manometric fluid, two different manometric fluids will be here. One is U-tube and other is, this is inverted U-tube and this is U-tube and U-tube. So again, you need two different manometric fluids eventually. That's obvious. So suppose because of this fluctuation was still here until here. So this will be mercury generally. Okay, rho m. And from here, let's suppose here, then it goes till here. This is also mercury only. Rho m. This much will be rho m dash. Okay, rho m dash. So suppose this level is y1. This level is y2. This level is y3. And from here, you go till y4. And then from here, y5. Okay, now you apply. You go starting from this down, then jump off, then above, then jump off, same liquid, then go down, then jump off, same liquid, go above, go above. Okay, so let's write. Then you are going down, your pressure increases, rho 1 G Y1. Then you jump off, rho M G Y2, go above. Then you go down again, rho M G Y3 minus rho, then you go above, rho M G Y4. Then you go above again, rho 2 G Y5 is equal to 2. From here you can get, sorry, here it will be rho M dash GY3. Okay, rho M dash GY3. So here you can get, you can ignore this because the deflection is also very less. And density of the gasoline is also less. Okay. So you get the pressure difference here. Right? Okay, I think I've covered all the pressure measuring devices, and in the next lecture we'll start with the hydrostatic forces. And I hope you all will be regular to your lectures. Our next tutorial will be on the day after tomorrow, Sunday itself, same time, 6 to 8 p.m. If you have missed any of my videos, tutorial videos, my YouTube channel name is YouTube name is Nptel with Varnit. Okay, you can check out all the PDFs I'll upload there in the video description. You'll see the Google Drive link, all the PDFs you will get. Don't worry about that. You can also suggest your friends or mates to join the video series which I'm taking, and although you can also subscribe to the channel and check out all my videos. I have also taught other two courses there. So someone has asked what kind of book. So there is no particular book, okay, standard book you can say always, but yeah, FM White is there for the fluid mechanics. Okay. from that author, I prefer FM White generally for the UG level. Or you can, another book for this particularly, there are a lot of books in totality, but I prefer FM White here for basic understanding. There are some higher level books as well. I don't suggest that at such a stage, but you should first, if you see my notes and everything, you will understand my lecture videos, you will understand very detail. Okay. So any other doubt you have, please ask. You can unmute yourself. Any doubts? There is one book. Okay, so we can end the session, but if you have any doubts, I'm staying here.